In this video, we'll find the center of mass. We'll find the location of the center of mass of a thin plate shaped like the domain D that we've been working with mass density given by rho of xy equals x. We'll find the location of the center of mass for this plate. We found before that the total mass of this plate was the integral of x dA, and that came out to be 14. Next, in order to find the location of the center of mass, next we need to find two more integrals. The location, the integral over the domain D of x times the density, and the integral of y times the density. First, let's find those integrals, and then we'll see how to use them to find the center of mass. So let's start with the first one. X times the density. Well, in our example, the mass density is also x, so this is the integral of x squared dA. Now, we can work this integral out in a couple of different ways. We could slice horizontally, we could slice vertically, or we could use polar coordinates. Any of those would work, and we can also take advantage of the symmetry of this domain. Let's work this out using polar coordinates. We saw that in this case, in polar coordinates, theta goes from minus pi over 2 to pi over 2. R goes from 1 to 2. Our function that we're integrating, x squared, well, x is r times cosine theta, so this is r squared times cosine squared theta, and dA is r dr d theta. This is a separable integral. I have a function of r cubed with constant bounds times a function of theta, and the theta has constant bounds. So this is integral from r equals 1 to 2 r cubed dr, integral theta equals minus pi over 2 to pi over 2 cosine squared theta d theta. The first integral is no problem, 1/4 r to the 4th from r equals 1 to 2. For the second integral, we can use a trigonometric identity. The cosine squared theta is 1 plus cosine 2 theta over 2. And then when we look for an antiderivative of that for the cosine 2 theta, then we can use the u substitution. So an antiderivative of cosine squared is 1/2 theta plus 1/4 sine 2 theta. That's using the identity that's written here, and then when we go to integrate cosine 2 theta, because of the u substitution, taking u to be 2 theta, we have to divide by 2 again, and that's why we end up with a 1/4 here. So that's how I found that antiderivative, and of course we can check by taking the derivative here and seeing if we get the right cosine squared theta. Let's see, theta goes from minus pi over 2 to pi over 2. Alright, so in our first factor we have 2 to the 4th, which is 16, minus 1 to the 4th, which is 1, all divided by 4. I don't know where that oval came from, that ellipse. Let's see here. Now we'll plug in theta is pi over 2. and when we have 1/2 pi over 2 plus 1/4 sine pi, and then we'll subtract what we get when we plug in theta is minus pi over 2. So we'll have a half times minus pi over 2 plus 1/4 sine minus pi. All right, well, sine pi is 0, sine minus pi is 0. This is 15/4 times pi over 4 plus another pi over 4. So in other words, pi over 2. And we end up with 15 pi over 8 for the value of this integral, the integral of x times rho. For the integral of y times rho over this domain, I'll show how we could start setting it up. So this is the integral of x times y dA. So integral from theta is minus pi over 2 to pi over 2. Integral from r equals 1 to 2 x times y. So x is r cosine theta and y is r sine theta. So if we multiply them, we get r squared cosine theta sine theta, and then r dr d theta. And we could continue on like this. It's separable again. We have another r cubed. This time, instead of cosine squared theta, it's cosine theta times sine theta. It's actually easier to integrate. And we could work through all this, but I'll tell you, back at this step here, or maybe at this step really, we didn't need to get into polar coordinates. This is just 0. Can you see why it's 0? Well, it's not on screen at the moment. If we go back up a little bit to our picture of the domain, this domain is symmetric with respect to reflection across the x-axis. Reflecting this domain gives us the same domain, but if we reflected, it would flip y into minus y. It would flip positive to negative and vice versa. It would flip y into minus y, but keep the same domain. In other words, that means that the top half and the bottom half would cancel out. Whatever we get from integrating y on the top half would cancel out with integrating y on the bottom half. All these positive y's and the minus y's cancel out. And that's why we get 0 in this integral. Okay, so for this integral with y times the mass density, because of symmetry, we see that we get 0 in the integral without having to do as much work. Okay, now that we've evaluated those integrals, we can use them to find the location of the center of mass. This is sometimes written x bar, y bar. It's just the average x value and the average y value. The average value of x and the average value of y, but these are weighted averages. Weighted by the density rho. So we get the total integral of x divided by the area or whatever, but with a rho in there for the density. And similarly, if it was just a regular average, then I would take the integral of y divided by the integral of 1 The integral of 1 would be the area, and the fraction that I've written here would be the normal average of y, but it's a weighted average with weighting function given by the density rho. Now that we've worked out all those integrals, we know that we have, 15 pi over 8, and the denominator is the total mass was 14 over 3, and the average value of y was 0. The integral was 0. Well, divided by 14 over 3 doesn't matter too much. So a lot of fraction stuff will cancel out here, and we end up with 45 pi over 112. Zero. And if we calculate out a little bit, let's find our handy calculator here. Okay, Desmos, what's 45 pi over 112? We get 1.26. On our original drawing of D, that's about here. So a quarter of the way between 1 and 2, roughly. So it's about there as the center of mass. It makes sense that it's on the symmetry line, that it's balanced between the upper and lower parts, and it makes sense that it's to the right of the geometrical center line, given that this object, this shape, goes from x equals 0 over to x equals 2. The midway line is at x equals 1, but our center of mass is to the right of that, and that makes sense because of the density being distributed more to the right. Remember, we said that the right-hand side was heavier than the left-hand side, and that's pulling the center of mass to that right-hand side. So this lines up with our intuition, the result that we found.
In these videos, we've followed a single example through various different ways to set up and evaluate the integral with horizontal and vertical slicing and polar coordinates. And we've seen how to use that integral to find the total mass of a thin plate, and we saw the role that symmetry can play, and we also did an example of finding a location of center of mass, all based on that one single example that we started with. I hope it's been helpful for you. Thanks for watching. Bye.